Okay, so in today's class we have to see how we can calculate capacitance for different types of capacitors. Mainly, we will discuss two very important shapes of capacitors: cylindrical capacitor and spherical capacitor. And then we will extend the idea of spherical capacitor to the idea of an isolated sphere. And then at the end, we will see how we can calculate the capacitance of multiple capacitors which are connected either in series combination or in parallel combination. So that's pretty easy lecture because most of the stuff we have already been done in last class. Okay, so let's start with the capacitance of a cylindrical capacitor. Um, Capacitance of cylindrical capacitor. Okay, so first of all, we have to draw a cross-sectional area of a cylindrical pipe. So assume that you are viewing the top end or the front end of a cylindrical pipe, and so let's draw that end. Yeah. Um, so this is one plate. Draw a little bigger, and there is another plate. Let me draw it a little bit more bigger. Okay. So these are the two plates of the capacitor. So say one plate carries the positive charges all over the surface. Say let's suppose so this inner plate has positive charge smeared over the surface, and this bigger circle has the negative charge. And the distance and both of these circles, both of these cylinders have different shapes, and the material between these two plates, between these two cylindrical plates, is an insulator, as required as required in capacitors. Okay, so um, um, so suppose say this is the central point. So from this center point, I can sorry. So if this is the central point, then I can say that this is the radii of the inner circle, and this would be the radius of the outer circle. So let me call this inner circle, the radius of this inner circle as A, and this will be B. This is just notations. You can change as you want. Now we have to also draw Gaussian surface. Um, and we draw the Gaussian surface around the positive cylinder. Okay, so let me draw this in a different color. Suppose this is the Gaussian surface, and we assume the radius of this Gaussian surface to be r. Okay, so let me draw this. So let's say the radius of this Gaussian surface is r. Um, and the direction of our integration would be reversed as we discussed later, as we discussed yesterday. So suppose to say this is the direction of our integration. Um, so we have to integrate from outer surface to the inner surface. So this basically it means that our limits on integration should be from B to A rather than A to B. Okay, now we know that how to calculate electric field. We derived this formula yesterday, epsilon naught EA, and the area of a cylinder is just 2 pi RL, where L is the length of the cylinder and it is also interpreted as H, while R is the radius to the Gaussian surface. Okay, so E comes out to be Q over 2 pi epsilon naught R L. So once we have calculated electric field, we can easily compute potential. So potential is written as minus to positive E ds. So we have to integrate other way around. So here B and A, Q over 2 pi epsilon naught 1 over RL, and we are integrating along the radial element. So this ds will be replaced by dr. So this is A, sorry. So let's take all the constants out of the integration. BA 1 over R dr. And we know that the integration of this integral, or the integrand 1 over R, will be simply natural log of R. Um, from B to A. Mm, are we doing it? Are we doing it right? So if since we are integrating from this side to this, so I need to put this sign because we are reversing the direction of integration. Fine. So since we are integrating in the reverse direction, so I had to put a negative sign here. Um, oh well, this is just fine. This is just fine. We are integrating from the initial to final value. Okay. So up till now we have calculated this term, and this will yield V equals minus Q over 2 pi epsilon naught L log of A minus log of B. So just think about this negative sign. You will figure it out. We have discussed a lot about this negative sign in the last class. So this is minus Q over 2 pi epsilon naught. Um, so let's take a negative sign out of this parenthesis. So this will become positive, and we will get log of B minus log of A. And this will yield Q over 2 pi epsilon naught log of B over A. This is the required potential. Now, it is easy to calculate capacitance. So C is equal to Q by V. So let's keep Q here by putting this factor over here, 2 pi epsilon naught, and log of B over A. Okay, so this Q will get cancelled out by this Q, and we will retain the factor of 2 pi epsilon naught as the numerator. C equals 2 pi epsilon naught 1 over log of B over A. So this is the required capacitance of a cylindrical capacitor. Okay, now so now in the same fashion we can also calculate the capacitance of a spherical capacitor. And interestingly, this calculation will remain the same. Only we have to change the area element in the calculation of cylindrical capacitor. Now you can see that this diagram can also serve the purpose of a three-dimensional sphere or a three-dimensional circle. So we can easily view this, and even we can safely view this as a pictorial representation of of the surface of a three-dimensional sphere. So we just have to change this element here, and rest will remain the same. So correspondingly, integration will also be changed depending upon this vector. So let's keep this diagram, and we know the rest of the process. So since Q will be epsilon naught EA, and in this case A will be 4 pi r square. Let's just draw the square radius of Gaussian surface, or any sphere, the radial element, and E will be Q over 4 pi epsilon naught 1 over r square. Now we know what we have to do. So again, V is equal to EDS. Let's keep all the constants out of this integration, and we have to integrate 1 over r square with respect to dr. Okay, so Q over 4 pi epsilon naught Q over 4 pi epsilon naught sorry, this is minus 2. So minus 2 plus 1, this is how we integrate. Oh, I forgot to put a negative sign here. And this will be, and we are integrating over the limits of b to a. So minus q over 4 pi epsilon naught. So this will just be r minus 1 over minus 1 b to a. This minus and this minus will turn out to be positive. So this is q over 4 pi epsilon naught and 1 over r. Okay, so the potential difference will come out to be q over 4 pi epsilon naught 1 over a minus 1 over b, or q over, this is just simplification, q over 4 pi epsilon naught a b over b minus a over ab. So this is the set potential for a spherical capacitor. Now we know how to calculate capacitance. C is equal to q by v. So this q over here, and we have for q over 4 pi epsilon naught b minus a over a b. Again, this q will be cancelled out by this q, and 4 epsilon naught will become the numerator since it's a fraction under a fraction, a b over b minus a. Okay, so this is the capacitance of of a spherical capacitor. You can see it is very easy to calculate the capacitance of any capacitor. You just have to figure out what the area would be. So if you can find out the area, you can compute the capacitance very easily. So the capacitance of spherical capacitor. Okay, so now let's see what the capacitance would be for an isolated sphere. And first of all, let's see what do we mean by an isolated sphere. So let's do it on the next page. Um, an isolated sphere is like a regular sphere. So, so let me draw this much bigger. So this is the first one plate of capacitor. And now the other plate would be very, very far away from the second plate, from the first plate. So, so say this is from this central point. This is A, and this will be B. Now you can see that B is very, very far away from A. So that is B is approaching to infinity. So basically, in an isolated sphere, we assume that um, B is very, 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 very greater um, than A. So B approaches infinity, and and let me call this A just the radius of the sphere. So it will just be a sphere rather than isolated sphere. So if I so basically we are assuming that the inner circle or the inner surface of the capacitor will just be like a UL sphere. So that's why I'm calling this just capital, or this is notation, nothing else. Now we figure out this formula for the sphere. Okay, so let me write here. So C equals 4 pi epsilon naught B A over B minus A. And see what happens if I insert these values here. So C over 4 pi epsilon naught infinity times R over infinity minus R. So this is infinity over infinity. What is, and this is completely insane. This is not a physical number. So it means so basically this is an indeterminate number. We cannot figure it out ever. So there is no way to see what this number means. So we can although though we know that if we divide a number by infinity, I will get a zero, or in turn if I divide a number by zero, I'll get infinity. So but what if I divide a number 0 by 0, I divide infinity by 0. I divide 0 by infinity. I divide infinity by 0. What is a 0 to the power 0? What is a 0 to the power infinity? Infinity to the power 0. Infinity to the power infinity. Basically, we cannot calculate these numbers. So usually we call these numbers as indeterminate numbers. It means this formula in this particular form is not going to work. So we have to modify this relation. So let's see how we can deal with such situations. So the capacitance is 4 pi epsilon naught B over B minus A. Let's take B common from the denominator. So this will be B into 1 minus A over B. Now this B will be cancelled out with this B, and you will get 4 pi epsilon naught A over 1 minus A over B. Now put the values. 4 pi epsilon naught R over 1 minus R over infinity. Any non-zero number divided by infinity will be 0. So the capacitance of an isolated sphere will turn out to be C equals 4 pi epsilon naught times R, just the radius of the inner sphere. So this is the formula for the capacitance of an isolated sphere. I hope it will clear the idea. Okay. Um, But I urge you to note one thing in all of the formulas that we have developed so far. Either they are for parallel plate capacitor, cylindrical, or spherical, or even this formula for isolated sphere. None of the formula depends upon either electric field or electric potential or electric charge. They just rely upon the geometrical factors. They only have constants like, so apart from epsilon, they have physical constants like which have the dimensions of length. So in this formula we have r. In this formula we have a, b. So both are the radii of the elements. So so that's just a dimension of length. Same is the case for the parallel plate capacitor. Also we have there a and b. And in the formula of parallel plate capacitor we have the factors of a and d rather than q, e, and v. So, so, so it shows that the capacitance of the capacitor just depends upon the geometric shape of the capacitor. So it means shape, it plays a very, very important role in deciding the capacitance. So that's why so that's one of the, so so this shows a convenience to use the Gaussian law here. So because we only have to integrate over a geometric factor. So that's pretty much convenience for physicists or engineers to do this stuff. Okay, so now let's do some calculations regarding the combinations of capacitors. So suppose we have a number of capacitors which are arranged in a parallel combination. Um, Capacitors in parallel. Okay, so let me draw. I'll try to draw this diagram. Let's see if it makes any sense. So suppose I have three capacitors over here. They are connected with the battery. So this is V. So this is capacitor number. So let me call this capacitor number one. This is two. This is three. This is positive plate. This is negative. So all these terminals will be, all these edges of all these plates of capacitor will get the positive charge. And all this will get the negative charge. Okay, now in a parallel combination, we know from the previous classes, same V potential remains same, but current will change. And if current will change, it means all these plates, all these capacitors will have different charges. So it means, so I can write that V1 equals V2 equals V3 equals V, but they will have different charges. So this plate will have charge Q1, this will have Q2, this will have Q3. So correspondingly, if Q is changed, then C will also be changed. So I can write that um, Q1 is equal to C1V, Q2 is equal to C2V, and Q3 is equal to C3V. So since we are interested in looking for the total accumulated charge over the plates of the capacitor, so basically we have to find the superposition of these charges, and this will yield the total capacitance, or as we usually call this the equivalent capacitance. So this will become C1V plus C2V plus C3V. So by taking V common, C1 plus C2 plus C3 into V. By writing it as so by taking this V over here, so let me call this equivalent capacitance, and this will be C1 plus C2 plus C3. So it means, or equivalently, for n number of capacitors, I can write C equivalent I from 1 to n summation Cn. So you only have to add the capacitance as a linear combination, nothing else, and that will yield. the capacitance in a parallel combination. So if we have three capacitors, we'll get this formula, and for any number of capacitors, we'll have this general relation. Here's similar stuff we can do for a combination of capacitors in series. Okay, so let's see how we can do that. Um, Capacitors in series combination. Okay, so we can draw the diagram as so. I think it would be better if I use a diagram like this. Um, yeah, that's okay. So so let me call this capacitor number one. This is two. This is three, and this is battery V. So since this capacitor is attached with the positive plate of a capacitor, so this will gain positive charge, and in turn this so all the negative charge. So as a phenomenon of induction, this plate will get negative charge. As basically this plate will get negative charge, and the corresponding plates the will get the opposite charges. This is according to the phenomena of conduction. um Sorry, conduction. So not conduction, it's basically this is according to the phenomenon of induction. So basically this positive charge will induce negative charge on the other plate, and this negative will in turn induce the positive charge over this plate, and the process goes on for all the capacitors. Okay, so in a series combination, all plates will get different number of charge, will a different voltage. So this will get V1, this will get V2, this will get V3. So basically we have different V, but we will have same number of current. So since so this plate will get the same number of charges as this plate, because these charges are produced by the phenomena of induction. So the number of charges should remain conserved, because this plate cannot induce more charges so then it has. So the number of charges should remain conserved. So same I, which means same Q. So but if V is gonna change, then capacitance will change. So it means I can write, so since C is equal to Q by V, so C1 is equal to Q by V1 plus, sorry, C2 is equal to Q by V2, C3 is equal to Q by V3. Okay, and since V is gonna be change, so I can write V is equal to V1 plus V2 plus V3, and V will be Q over C. So this will be Q over C1 plus Q over C2 plus Q over C3. So V equals, by taking C common, 1 over C1 plus 1 over C2 plus 1 over C3. So by taking V and C's other way around, so this so by keep so, so let's bring this V over here as a denominator of Q, and let's take this parenthesis on the left hand side. So this will be 1 over 1 over C1 plus 1 over C2 plus 1 over C3, and this will be equivalent capacitance. So using this, I can define a more familiar relation, that is, um, let's do all this stuff here. So I have written C equivalent. So let's invert all these terms. So this will become 1 over C, sorry, 1 over C1 plus 1 over C2 plus 1 over C3, or for any number of capacitors, 1 over C equivalent will be I from 1 to n, so 1 over Cn. So this is just mathematics. So between these two, so we just use preliminary algebra. So you can figure this out. And this is the capacitance of a parallel plate capacitor. Using these two formulas, we can calculate, using this formula we can calculate the capacitance of three capacitors, um, joined in a series combination. While this formula will give us will while this formula will give us capacitance of any number of capacitors if they are joined in a series combination. Oh, so that's it from this lecture. Okay, thank you.